Okay, today we're looking at understanding logarithms and basic log functions. First things first, what we need to understand, the most basic thing to understand about a logarithm is that the log is the inverse of the exponential function. An exponential function looks like this. It is y is equals to a raised to the x power, where a is greater than 0 and a cannot be 1. A logarithm looks like this. It is y is equals to log base a of x, where again the base a has to be greater than 0 and a cannot be 1. This is what a logarithm looks like. Now, before we go any further, let's try and just get a basic understanding of how logarithms work, why logarithms were formed. And so let's see if we can compare the exponentials and the logs a little bit more closely. So on this side right here, I have what I'll call exponential form. On the other side, I'll have what I will call logarithmic form. And so, where was that right? Oh, where'd it go? So let's say I have exponential form over here and log form. Let's take a basic exponential that we know how to work with. Let's say I have right here 10 to the third power. Well, 10 to the third power is 10 times 10 times 10, which is 1,000. And so this right here will be equal to 1,000. Well, the log form of this expression right here starts with the base. And so we will write log base 10. And so this is saying right here, this is the log, but this log right here is considering when we started with an initial base of 10. And then what happens is that these two numbers switch places. And so it'll be log of 1,000 is. Now let me read this equation. Log of 1,000 is 3. What this statement right here is saying is this. This is read log base 10 of 1,000. And what this is saying, well, if I took 10, what power do I need to raise it to get 1,000? That's the answer. That answer is 3. So in a logarithm, the answer you get is the power. Equals, the answer you get is the power. So again, let's try again. So let's say I have 3 to the 5th power, and 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, 81 times 3 is 243. If I want to express this right here as a logarithm, I would simply go log, L-O-G, and then say, what base am I looking at? The base I'm looking at is 3. And then, well, log base 3 of 243 right here is what power should I raise 3 to get 243? And that answer right here is 5. Alright, one more example, quick example. If I have, say, 2 to the 6 is equals to 64, and then therefore log base 2 of 64 is equals to 6. So some key things right here. The base is very important. If I were to change the base, I would need a different power, correct? But another thing to understand, that this is not saying 2 raised the 64th power. That's not what the log is saying. The log is saying log of 2. This, you can think of this right here as the first half of the logarithm. A log of 2 right here is saying the base of interest, and the log right here says I'm interested in the power. Log base 2 of 64. And again, it's important to see this as one whole term. this right here, log base 2, has no meaning. It has to be log base 2 of something. So log base 2 of 64, and again, the power that I need to raise 2 to get 64. An example of why the base is important is if I have, say, log base 2 of 4 of 64, clearly the answer no longer can be 6, because 4 to the 6th power is not 64. In fact, the answer right here is going to be 3. So as I change the log base, the answers will change what the log evaluates to. Now, an important ability to have when it comes to log and exponentials is switching between the two sides. If I have a log, converting it to an exponential form. If I have an exponential form, converting it into a log form. So let's look at that right now. So, converting between b/w, logs and exponential form. So, let's see, I have right here an expression. Log base 3 of 81 is equals to 4. And I want to convert this to exponential form. Right? So I'm starting over here on the right side and I'm trying to go over to the left. Well, when you look over here on the left, the first thing you see is that there is no word log. I don't actually write the word log. And so the first step right here in converting this to exponential form is to simply drop the log. So the first thing to do is drop the log. So I am no longer going to be using the word log. The second step is very simple. Take the base to the other side. And what I mean by this is the 3 now becomes the base, but the base on the other side. And so what I'm left with when I take this 3 and I carry it over, let me see if I can take this 3 and carry it over. Let's see if I got some skills today. If I take this 3 right here and I carry it over like so, what I get right here in my result is that 81 is equals to 3 to the 4th power. So you're going to take the base, over to the other side. So 3 is still the base, but now it's on the other side. And yes, indeed, 3 raised to the 4th power, 3 times 3 times 3 times 3 is indeed 81. And so I've converted this to the exponential form. Let's try a few more examples. One of the most important reasons for this rule, converting to exponential form, is that it allows us to solve equations involving logarithms. Let's say I have log base 4 of x is equals to 2, and I want to find x. Well, if I simply convert to exponential form, I will solve the problem immediately. Again, I drop the log, and I take the base to the other side, and that leaves me if x is equals to 4 raised to the 2nd power. Again, 4 will always be the base. So I mean, keep in mind, 4 is the base here, it will always be the base. Well, what's 4 squared? 16, and that's the answer to my problem. Look at that. Solve the log equation just like that. Another example, if I have log base 3 of x minus 2 is equals to 3 right here, and I want to solve this equation, drop the log, take the base to the other side, x minus 2 is equals to 3 cubed, x minus 2 is equals to 27, so x is equals to 29 after I add 2 to both sides. Interestingly enough. Sometimes we just want you to write the log as an exponential, and so we just give you all letters, and they say, well, this is a log expression, please write it as an exponential form. And so what we will simply do is we will simply drop the log and take the base to the other side. A is equals to z to the m power. I have the power. And that's my answer right there. Now, let's look at going the other way. Let's say, now I'll actually later on show you a second way, but I'm just going to show you to basically undo what we just did right here. So let's say I have um, 125 is equals to 5 cubed. This right here is the log form of the expression, and I want to convert this back to logarithmic form. All I have to do is take the 5 back over and add the keyword log back in. Right. Just do exactly the opposite. So I will take the 5 back over and then add in the word log. And so I will get right here log base 5 of 125 is equals to 3. Just like that, I have converted back into logarithmic form. Anyways, again, like I said, we'll do more examples of this one a little bit later. But for now, you just go understand that you're reversing the process that we did right here. Now we need to stop right here and then handle a point of some information we need to know. And those are your common log and your natural log. A common log is a log of base 10. Your natural log is a log of base E. Remember E, that special number, 2.71828? E is that number right here. Well, if I have log base 10 of x, I simply do not write the 10 down. Every log must have a base. Remember, base must be greater than 0. Base cannot be 1. Every log must have a base. So if we do not see a base, that means the base is 10. It's there, we just don't write it down. Similarly, if I have log base e of x, I use a shorthand, and that shorthand is ln of x. I believe it comes from French. In French, you'd say log natural. So you'll say log first and then natural instead of natural log natural. The noun comes first, I guess. I don't know. And so because of that, we write ln. Again, ln of x, say ln of 50, simply means log base e of 50. But again, we just don't write the log base e because it takes some time, I guess. I also think that back in the day when we were using typewriters, people got tired of putting all those subscripts in by hand. And so they say, we'll just not write it down. They'll know what we mean. So you need to know what we mean now. Alright. So, now that we know a little bit about logarithms, let's look at the basic rules that all logarithms follow. We call those the properties of logs. These are things that are always true for all logarithms. The first property is that a log of any base of 0 is always undefined. You cannot plug a 0 into a logarithm. Similarly, log base a of a negative number is undefined. I.e., if I plug in log of negative 72, there is no answer. These two combined tell us that the domain for all logarithms are numbers that are greater than 0. Domain is from 0 to infinity. Logs only take positive numbers, i.e. 0 and negative numbers are out of there. If I plug 1 into a logarithm, any logarithm whatsoever, the answer is 0. By the way, this is one that professors love to use, log of 1. Since the evaluation is so simple, it's definitely one you want to memorize. Property number 4, if the base is what's the log being evaluated at, then the answer is automatically 1. Log base a of a is 1. So a quick example, if I take log base 17 of 17, then this is 1. I.e., if I take 17, this is asking right here, what power should I raise 17 to? what power should I raise 17 to get 17? Well, that power must be 1. Yeah, yeah, yeah. The last two properties right here are the most valuable properties of logarithms, the most indispensable property of logarithms. Log base a of a raised to the nth power. If you look carefully right here, I have a logarithm, but I'm plugging into the logarithm an exponential. Logarithms and exponentials are inverse functions of themselves. And so what will happen is that the log and the base of the exponent will cancel out, leaving me with the simple answer of n. This is a very powerful result and allows us to evaluate many logs very easily. Consider log base 3 of 27. Well, this is the same thing as log base 3 of 3 to the third power, correct? Yes, because 27 is 3 times 3 times 3. And then all of this nonsense cancels out. So log base 3 of 27 is actually 3. And you think about it for a second, what power must 27 be raised to? What power must 3 be raised to get 27? Well, this is the power that 3 must be raised to get 27. Similarly, there's the reverse of this operation, and that is if I take a base and the power has a log of the same base, the answer again will be n. The log and the exponent, again, so this right here is the exponential, this right here is the log, they will cancel each other out. So all I'm left with right here is just the power of n. The key thing is the bases must be the same. Once we have those right here, then we are in business. So for instance, if I have e raised to the ln of 27, e and ln are bases of the logs and exponential of the same base. They will cancel out. So my answer is simply 20 and 7. Look at that, look at that. Alright, so those are our 5 properties. The last 2 in particular are very important. So you definitely need to know the last 2. But the other ones are really shortcuts, again, answers quickly for logarithms. Let's go ahead and practice a little bit with those properties to help us get a better feel of how those properties come to life. So, sample number 1. Let's ask you to evaluate log base 2 of negative 5. In fact, I want you to evaluate all of these without a calculator. Later on, I think I'll get to the point where I can show you how to do things with a calculator. But for now, we don't need no calculator. Well, log base 2 of negative 5. I know that if I plug a negative number into a logarithm, I don't get an answer. So log base 2 of negative 5 is undefined. Just like that. Just like that. Let's try again. Log base 5 of 5. Well, what does this evaluate to? Well, when these two numbers are the same, the answer is 1. So log base 5 of 5 is just 1. Say log base 7 of 0. Can I plug a 0 into a logarithm? The domain are only positive numbers. 0 is not positive. And so therefore this is also undefined. There is no answer here, people. There is no answer here. Number 4, log base 18 of 18 to the 5th power. Well, I don't know what 18 to the 5th power is. It's a good thing I don't care, right? Because I know the log and the exponential function will cancel out. So all my answer is going to be 5. Just like that. Similarly, if I have 12, raised to the log base 12 of 78. My answer is 78. Pretty easy, right? Pretty easy, right? Alright, let's go into some questions that are a little bit more difficult. And because they're a little more difficult, we'll be showing you two ways to solve them. Um, let's say I have this right here. Well, I get log base 4 of 64. And I am trying to figure this thing out. Again, I ain't got no calculator. All I have are my properties of logarithms and the knowledge that we've gained. I'll show you two ways of working it out. The first way is not straightforward, but I think is very efficient, especially when these things start getting complicated. Right here, let's just say I don't know what the answer is. So if I don't know what the answer is, I can just set it equal to x. And what I have done is I have simply created an equation. And now I need to go ahead and solve this equation. Well, how do you solve a log equation? Remember, whenever you have a log equation, you convert it to exponential form. And that's two steps. What you do is you drop the log and you take the base to the other side. And so therefore, 64 is equal to 4 to the x power. Now, from our study of exponential functions in the last section, I know I have to ask myself, well, are the bases the same? No. So can I make them the same? And the answer is yes. 64 happens to be 4 to the third power. Well, 4 to the third power. My bases are the same. And so that should be an x over here. My bases are the same, and so I can break out my ninja blades and cancel my bases. And so that tells me that x is equal to 3. So this logarithm right here evaluates to 3. That is the answer. The second method right here uses the properties more directly, but it normally is for students who are familiar with their powers. This is the key step right here. I know that 64 is 4 to the third power. And because I know that, I can say, well, this is actually log base 4 of 4 to the third power. Notice right here how I've changed the 64. And then the bases are the same. When the bases are the same, they cancel out. So my answer is simply 3. 3, 3, 3, 3, 3, 3. Let's try another one. Number 7. Let's say I have log base 4 of 1. Well, you should immediately know what the answer is. Log base 4 of 1 is 0. That's one of our properties. But if you've forgotten, you simply set it equal to x. And then you say, well, drop the log, take the base to the other side. 1 is equals to 4 to the x power. Are the bases the same? No. Can I make them the same? Yes. I can write 1 as 4 to the 0 power. Or I can tell myself, well, what power must I raise 4 to get 1? The only possible number is 0. So therefore x is 0. Like I was saying, you could have just used our foreknowledge from, way back in the past. That log of 1 is 0. Or we could have worked it out. An extension of this using our log basis, if I have log base 7 raised to the log base 7 of 48, well, clearly the answer is 48. Similarly, if I had e raised to the ln of 92, the answer is simply going to be 92. Because the e and the ln cancel each other out. Again, similarly, I guess I should write a 9 here and a 10 here. If I have ln of e to the 5th power, the answer is simply going to be 5. The ln and the e cancel each other out. They say, sayonara, see you later. And then they just go walking off. Just all rude like that. Just go walking off. Another example. Number 11. Let's say I have log base 5 of 125 is equals to, I don't know, gotta evaluate this without a calculator. I'm just going to say equal to x. Convert to exponential form. You're going to get tired of converting to exponential form after a while. Drop the log and take the base to the other side. And just like we did from way back when we're doing our exponential equations, do you see a fraction? Yes, I do. So whenever I have a fraction, I write it with a negative power. Remember back in them days? Negative power. And then, well, 25 is 5 squared. When I have a power to a power, I multiply. And so that's 5 to the negative 2 is equals to 5 to the x. Again, when you get good, you can actually skip from this line to this line. 5 squared is 25, but it's upside down. It's flipped. And so therefore the power needs to be negative. But for now, I take it step by step. Now, I can break out my ninja stars and say goodbye to the bases. Cancel those out. And so then what that tells me is that negative 2 is equals to x. And so this log right here gives us an answer of negative 2. Which gives us a very important rule right here. For a log with a base that is greater than 1, to get a negative answer, I have to plug in a fraction, a proper fraction into the logarithm. Because that fraction is what's giving me that negative power. And that negative power, because remember, that's what we care about, is that negative power. Again, to solve this problem the other way, log base 5 of 125, you have to know that log base 5, 125, 1 over 25 is 5 to the negative 2. Once you know this fact right here, by going through these 3 steps, you know that they cancel out, and so the answer is negative 2. Okay. This is advanced at the beginning, but after you practice these a few times, you start picking up on the patterns and realize, oh yeah, my answer is going to be negative, and I got a 25. And so that's enough to take me home. Number 12. Let's say I have log base 3 over 4 of 27 over 64. That looks interesting. Well, 27 kind of goes to the 3 and the 4 kind of goes to 64. But I'm really still not sure what to do. So I'm just going to set it equal to x. Convert to exponential form, drop the log, take the base to the other side. And so that's 27 over 64 is equals to 3/4 raised to the x power. I don't know about you, but I know that 27 is 3 cubed. And 64 is 4 raised to the 3rd power. And I know I can factor out powers, so that's 3 over 4 raised to the 3 is equals to 3 over 4 raised to the x. And so therefore x is equals to 3. I need to raise 3/4 to the 3rd power to get 27 over 64. Again, it's important to be able to understand the meaning of the answer. When I get x equals 3, it means 3/4 needs to be raised to the 3rd power to get 27 over 64. Alright, number 13. We've done quite a few of these. Let's look at an interesting one. Let's say I have log of radical 2 of 8. What does that evaluate to? Well, once again, I don't know. So I'm going to set it equal to x, drop the log, take the base over. 8 is equals to radical 2 raised to the x power. Again, before when we had a fraction, it means a negative power. When I have a radical, it means a fractional power. And so this is actually 8 is equals to 2 raised to the 1/2 power to the x power. These two things get multiplied. And 8 is 2 to the 3rd power. Yeah, hopefully you start to get accustomed to your powers. Of 2, your powers of 3, your powers of 4, e powers of 5, e powers of 6, e powers of 7. Ignore me, I mean e powers of 10. That's normally how far we need to go. And of course, these cancel that. And I have a little bit of an equation to solve. I just multiply by 2. And so x is equals to 6. The radical 2 raised to the 6th power gives me 8. Crazy, yeah? But yeah, that's what it is. That's what it is. In truth and in fact, whew, we're almost there. Been a long go so far. Number 14. Let's say I have log of 2/5 of 125 over 8. Well, this kind of looks like one we did before. But I'm feeling a little cautious today. Well, so I got this lovely thing right here. 125 over 8 is equals to 2/5 raised to the x power. After I convert to exponential form, 125 is 5 to the third. 8 is 2 to the... Look, this is going really good. I know I can factor out the 3. 5 over 2 raised to the 3 is equals to 2 over 5x. And so I can wait a minute. Base is not the same. What am I supposed to do in this situation? Aha! But look, the bases are almost the same. I need to flip the base. How do I get a reciprocal again? Oh yeah, you need a negative power. The negative sign does not mean multiply. The negative sign means flip the base. Now my powers are the same. Now I can see that x must be -3. -3. Alright, 2 more key examples. Let's say I have log of 0.001 and I'm trying to evaluate this logarithm. Well, equals to x, I guess. I clearly don't know what the answer is. But, what's the base? Oh yeah, that's right. Well, there is no base. The base is 10. So there's a 10 right here that they don't write down. So I drop the log, take the base to the other side, and I have 0.001 is equals to 10 to the x power. Well, 0.001, that right here is a fraction of 1 over 1,000, right? Or, even better yet, I have to move the decimal point 1, 2, 3 times. So in scientific notation, when we move the decimal point to the right, we get negative powers. That's going to be 10 to the -3. Now that I have that, these cancel. X is equal to -3. Log base 10 of 0.0001 will evaluate to -3. Forgot what number I'm on. 15. Last but certainly not least, number 16. If I have ln of 1 over e to the 4th power. Well, you might be thinking, well, I see an L and I see an E. But the E is in the denominator. So I got to bring that E up first. And so that's just going to be ln of e to the -4. And for this example right here, I don't actually need to say I don't know what the answer is. Because ln and e are inverse functions. So you cancel each other out. And so my answer is clearly -4. Alright? That's lots of stuff for you to read. Enjoy reading, listening, and taking notes.